Hi everyone, I'm Cian, and today I'm going to be going over research conducted during my honours year at the University of Sydney. My project was titled The Interplay of Tectonics, Eustasy, and Surface Processes on the North Slope of Alaska Since the Jurassic. The motivation for this project was in trying to better understand the evolution of sedimentary basins in terms of erosion and deposition in the context of sea level change, uplift and subsidence, and other processes. So the North Slope of Alaska, as seen here, is a type of setting where the processes mentioned before, sea level change as well as uplift and subsidence, can be explored. The North Slope of Alaska is part of a small tectonic plate located within the Circumarctic and has had a diverse geologic and geodynamic history. It was originally up against the Canada Arctic Islands over here, and in the early Cretaceous, around 142 million years ago, it rotated counterclockwise as a result of the opening of the Canada Basin and collided with an oceanic island arc. This resulted in the formation of the Brooks Range origin, as seen here, and an adjacent foreland basin known as the Colville Foreland Basin. So the primary aim of this project was to investigate the effects of tectonics, including deep mantle flow and eustatic sea level fluctuations, on the landscape development of the North Slope of Alaska to better understand its evolution since the Jurassic. In order to achieve this aim, landscape evolution models of the North Slope of Alaska were run using the surface process modeling code PyBadlands. The vertical plate motions that were incorporated into the model include time-dependent dynamic topography estimates that were calculated from mantle flow models driven by plate tectonic reconstructions and used as boundary conditions for the models. Also, a series of tectonic events that were derived from paleogeography polygons, which were constructed in G-plates and could be assigned uplift and subsidence values, were incorporated into the models. The resulting model can be seen to the left and shows erosion and deposition through time, where deposition will be shown in red and erosion will be shown in blue. Sea level will be shown in white, and the drainage patterns are overlain and shown in light blue. To the right is the start time of the model at 120 MA, highlighting the main geologic features. The models capture the erosion of the Brooks Range origin and the Chukotkin Highlands to the west here, as well as the eastward to northeastward directed sediment dispersal across the Colville Foreland Basin, eventually overstepping the Barrow Arch Rift Shoulder, or the Alaska Rift Shoulder over here. The model also captures another uplift events on the eastern end of the Brooks Range in the Paleogene, which resulted in northward directed sediment dispersal over the eastern end of the Alaska Rift Shoulder. These mentioned depositional trends and provenance areas are similar to those observed from the sedimentological record. West to east cross sections across the Colville Foreland Basin were also taken at 90 MA to further examine the evolution of the shelf margin during the main phase of deposition in the basin, which was from 120 to 90 MA. From the cross section, it can be observed that the model captures a shelf margin trajectory shift at approximately 105 MA, where the progradation rate can be seen to significantly slow and the straddle stacking patterns shift from dominantly progradational to more aggradational. This shift can be observed in the sedimentological record, and the timing of this shift is consistent with dating performed by Lees et al., who dated the shift to occur between 108 and 105 MA. This trajectory shift and slowing of the progradation rate coincides with a relatively steady rise in sea level from 108 to 95 MA. However, the model also highlights that a dynamic subsidence of at least 50 meters from 110 to approximately 100 MA, which would have resulted in increased accommodation space within the basin, also likely played a role in the shelf margin trajectory shift observed at 105 MA. This study also marked an important step towards coupling tectonic reconstructions with landscape evolution models by incorporating horizontal plate motions into the models. Here is a model of the North Slope of Alaska and surrounding regions, which incorporated horizontal plate motions showing elevation through time from 150 MA to present. You can see The model captures the opening of the Amerasian Basin and a collision to the south, forming the Brooks Range origin, and subsequent deposition into the Foreland Basin, which is forming here. This is still a work in progress, and future work involves coupling the surface process models with the G-plates deforming plate motion models of Muller et al. To capture time-dependent lithospheric thickening and thinning events.